Alrighty, so back to Calculus 1, right? Okay, so Calculus 1, we're going over continuity at a number. This is where we left off yesterday. Definition, removable discontinuity. Let f be a function that is defined everywhere on an open interval. So now, class, let me see your hands. Okay, what does an open interval look like? Okay, that's one way of doing it. Okay, so now, so go ahead, right there, open interval. See what she has? She has open dots for the open interval. Yeah, now you're just being weird. Okay, yeah, don't do that. Okay, so now it's parentheses that we're actually using here. Parentheses are open intervals, and closed parentheses are brackets. Yeah, that hurts my hand. Anyway, so yes, you got because you like contort your hand to get it to like make it a square shape. So brackets are closed, parentheses are open. Okay, parentheses are open. Now, what that means is, now an open means I am not including the endpoints. Closed means I can include the endpoints. So bracket, yes, endpoints, parentheses, no endpoints. Okay? All right, open interval containing C except possibly at C. Okay? So the number C is called a removable discontinuity of f if the function is discontinuous at C, but the limit as x approaches C if f of x exists. So the limit exists. The discontinuity is removed by defining or redefining the value of f at C to be the limit as x approaches C of f of x. Now, it's exactly what we did today on our warm-up. On our warm-up where we had that problem. Let's see. Okay. Now, on this problem right here, I was able to remove the discontinuity of x minus 3, right? Because that gave me 0 in the denominator. So by multiplying by the conjugate here, I was able to remove the problem in the denominator by factoring it out, right? Okay, so that's called a removable discontinuity. So the limit exists, but the function does not exist at that point. All right, let's see. Continuity at a number. Determine whether a function is continuous at a number. Determine whether the floor function, f of x equals, okay, that's a floor function, is continuous at 1. Now, I'm going to show you guys on your calculator, so I know you guys all have those. Write me out. So, I'm going to go to a floor function right here, f of x. Now, it is, I can't remember where it is on this one. All right, so the floor function is called integer, int, parentheses, put my x, close. Okay, so this is how you actually type that in there. So it's integer x. So from my notes right here, yes, if you notice, it's not an absolute value symbol, is it? You guys paying attention?
Yes.
Okay, so it's not an absolute value. Now, I hit enter. Okay, this is a step function. Now, it's asking, determine whether the floor function is continuous at 1. Okay, so I'm going to take my menu trace, okay, 0, it's at 0, right? Still at 0, 0, okay, I was trying to, let's type in 1. Where's 1 at? 1 is at 1, 1. Okay, let's try the other one. Let's go 0.999. That's what I was trying to get to, but all right. Hey, look, it's down here at 0.999. It's down here, isn't it? So 0.999 says my thing actually estimates it, or it rounds it to 1 because it's so close anyway. So it's down here at 0.999 at 0, but when I just type in 1, it goes up. Now, what has to happen for something to be continuous?
Everything has to touch.
Both left and right hand sides, right? Okay, for it to be continuous, remember the roller coaster. You can't have any holes in the track, right? So, right there on the track, do both sides right there go to that spot? Right here.
Oh.
No, it's not. Okay? The left-hand side is not going to the same place as the right-hand side. But what if I were to say, hey, is it continuous at 1/2? Could I say it is? At 0.5, I could say it's continuous because the left hand and the right hand are going to that spot, right? And does that spot, is f of c the same value? Say yes.
Yeah.
Yes. F of c. So the 0.5 gives me 0. The limit of this is going to be 0 because the left hand and right hand both go to 0. Right? Left and right both go to 0. And the function is equal to 0 at that point. That's what it means for it to be continuous. Alright, so here's another graph right here to show what it's actually saying. So the floor function means it's rounding all the way down for every integer. It's rounding down for every integer. So at 0, it's actually starting at 0. There's a closed dot. Okay, it is 0 at that point. But once it gets to 1, that's an open dot there, and it jumps up to here. So once it gets to 1, it's the next integer. It's the next integer, so then it stays 1 until it finally becomes 2. That's what the floor function is. It always rounds down until you get to the next number. So it's not including 2 because 2 is up here. It goes all the way to 2. There's your open and there's your closed. It's going all the way to 2 but not including 2 here. 2 is included up here on this next one. Does that make sense or no?
Yes.
Yes? Kinda? What part of kinda?
I think I get it. I'm not sure. So like basically, if it's at like 1, then it's only like 1.
Yeah, so if it's 1 point anything, the value is 1.
Okay.
That's what it means.
All right.
All right, so let's take a look at the next one. Okay, definition: one-sided continuity at a number, let f be a function defined on the interval a to c. So this one right here, okay, this is one-sided. So which one is included? C is included, A is not. Okay, then f is continuous from the left at the number c. So this is going from whatever value over here to my c value here. So from the left-hand side, if it is continuous here, I get f of c. Okay, next one. Let f be a function defined on an interval c to b. Now, which one is it including here?
B.
Nope, look at the bracket. The c, right here, the c is included. So c is included to b. So then f is continuous from the right. So from only the right-hand side. Okay? So if I were to look at this again, right here. So at this point right here, from the left-hand side, is this continuous?
No. Yeah. Yes. Isn't it
This one's a no.
No.
Why would this one be a no? Is this number included?
No.
That's why. It's a no because this number is not included.
So continuous is more like.
All the way continuous. There is no holes, gaps, jumps. Okay? So now let's look at this one here. So is it continuous from the right side here?
Yeah.
Yes.
Yes, from the right side, it is continuous here because that is a closed dot there. Looking at my notes, okay, it has to be a closed, right? It has to include the C, okay? My previous one did not include, dang it, there. From the left-hand side, it does not include the C, but from the right-hand side, it does include it. And my C value right here would be 1. Does that make sense? Are you guys okay now? Hopefully it helps. Okay. All right, so here's a bunch of just basic things about continuity on intervals. And pay close attention to where the bracket is for all these. Okay? Joy. All right, so let's take a look at determine intervals to which a function is continuous. Now, I think I could zoom this one a little bit more. There we go. Now, for this one right here, if I'm looking at this, here is an example. F is continuous only from the right-hand side, isn't it? It is continuous only from the right-hand side. Okay? From the right going left. Because this is my closed dot, right? That is the open dot. So that means that it is only continuous from the right-hand side. Now, for this one right here, this one is not continuous from the right hand or left hand. Okay? So left hand or right hand, but it is continuous on the open interval. That means that here to here. So we're not doing a one-sided, this is an open interval. So it's not including those. It means that everything in between, okay, that's what the parentheses, everything in between is continuous. Now the next one says F is continuous on A to B. Now, B is included. So this is going to be continuous from the left-hand side, right? From the left to the right, left-hand side, this is going to be continuous here.
Is there going to be a certain way we have to write that?
You mean just like this?
No. So that means like continuous?
This right here. Okay, so which part are you talking about?
I don't know.
So you would say, is this continuous? So now the limit as x approaches b from the left-hand side, so from the left of the function f of x is equal to f of b. So that means that f of b, this is this point right here, is included.
You know what I'm saying? Like, is there? Do we just write it like f is continuous on?
Yeah. Oh, yes. Over this interval here.
Yeah.
So you'd use bracket and parentheses. Okay. So there's a parentheses and there's a bracket. So bracket for including, parentheses for not included. Okay. Let's look at this. Now, this one right here. If you notice, it's got open dots on both sides, right? Open dots on both sides. So that is only continuous on a open interval. Okay? It is not continuous at either end. Yes, there is a point down here, but it's not continuous at either end, right? So think of it, that roller coaster again. If you go on a roller coaster and all of a sudden some point, it's like 5 feet down lower, you'll probably freak out, right? Okay, you don't want a hole in your track. Okay, last one.
Isn't that the same as?
What's what?
Aren't they the same, B and D?
B and D.
Mm-hmm.
The last, okay, B.
No, like
No. This is
number 2.
A. This is looking at A. Okay, A is this first one right here from the right side. So A from the right side. So going from the right side, it's not equal to there, right? So it's only continuous on the open interval. This is actually looking at the end point over here. So this is looking at the right-hand side. Okay, so from the left side, it is not because it's down here. It's similar though, it's just talking about which side it's going to be on. Because yes, there is a closed dot on this side, but it's not including it. Okay? Alright, now over here I have closed dots on both sides, right? So being closed dots on both sides, that means that both sides is included. So that means this is continuous on a closed interval. Right here, closed interval. It is continuous from the left-hand side going to A, and wait, no, sorry. Left going to B, and from the right going to A. Okay? Does that make sense? I'm hoping, clarifying a whole bunch of this. Okay, so now I have to change this back to, there we go. Okay, so keep going here. We have determined whether a function is continuous on a closed interval. Is the function f of x continuous on a closed interval? So whenever you're doing this, okay, let's see. We got to find some place in which that there's going to be holes in this. Given this right here, what would, interval, interval. There we go. Wait, come on. There we go. Every time you hear that, like, beep, beep, you know, my screen turns off and I have to re-click that button again. I can always forget. Anyway, so this thing right here, what's the domain of that? What can I not have there?
Negative.
I can't have negative, right? Whenever you see a square root, I cannot have negatives, right? Since I can't have negatives, that means that my output cannot be negative, right? So all my answers coming from there has to be positive, right? Can it be equal to 0? Okay, so let's figure out what this would be. So let's say that this has to be greater than equal to 0, right? So what type of dot would this symbol right here be? Is that open or closed? Closed, because it is equal to, right? Okay, I'm allowed to have a 0. The square root of 0 is 0, right? I'm allowed to have that, so I'm allowed to have a 0 there, okay? So how would I undo a square? Or, I'm sorry, how do I undo a square root? Square. Square both sides, so you get 4 minus x squared. Still 0. Okay, subtract 4, right? So negative x squared, negative 4, right? Okay, so it's going to be x squared. Change it, right? And positive 4 now, right? Because I divided by that negative. And so now how do I undo that?
Square root.
So x equals plus or minus 2. Okay. That just so happened to be my endpoints here anyway, right? So I look to see if there's anything inside there that would give me problems. Any holes, any place in which that I cannot have. I cannot have i's, can't have divide by zeros, can't have any of those. Okay, so now that just takes me to here. Okay, I'm all right, that's on that interval. Now I have to check my endpoints. So let's plug it in and see what we get from my endpoints. Okay, for it to be continuous on that, it has to work for both of those. So if I plug in negative 2, what do I get?
0.
So f of negative 2 gives me 0. Is that allowed? Okay, yeah. And so f of positive 2, we get 0. Hey, is this going to be continuous? Yes. Is it continuous on a closed interval? Yes, because it's equal to right here, right? It's equal. I'm allowed to have those. I'm allowed to have those there, right? So yes, it is equal. Okay, so this is continuous on a closed interval. If it was open interval, I would not be able to plug in the endpoints here. Okay, the endpoints would not be. Endpoints would actually be undefined or something. Continuity on a domain. Continuous at every number C in domain. Determine its function. It's continuous on its domain. Okay, what can I not have on this one right here?
Negative.
Can't have what? Can't have negative? Okay, so if I were to throw in a negative number in there, right? Can I throw in negative 1?
Yeah.
Yeah.
I can throw in negative 1, right?
Yeah.
No.
Yes.
You can. Because it's going to be -2.
That would be negative 2, wouldn't it?
Yes.
Can I throw in 0?
Yes. No. Yes. Yeah. Yes. Yes.
Why yes 0?
Because x squared is
0. This is 0, and 0 times anything is 0. Okay, so that gives me that, but I'm not allowed to have negative 1. So I can't have anything less than that, right?
So it has to be equal to the greater than 0.
x small.
Okay, so I can't have anything less than 0. Okay, nothing less than 0. Because that means I would have i's in there. That would be imaginary numbers. Okay, determine a function is continuous on its domain. My domain would be from 0 positive, right? From 0 to positive. So that would be the domain here. Polynomial function is continuous on its domain. All real numbers. A rational function is continuous on its domain. If a function is continuous on its interval, its graph has no holes or gaps on that interval. If a function is continuous on its domain, it will be continuous at every number in its domain. Its graph may have holes or gaps at numbers that are not in the domain. So what that means is, if I'm only looking at the domain of this, I'm okay. But if I'm looking at negative numbers over here, if I try to graph negatives for some reason, you would end up with messy, right? Okay, imaginaries. Same rules that we've gone over. Just how to plug it in. All right. Yeah. Okay, intermediate value means how did the chicken cross the road? That's intermediate value. How did the chicken cross the road?
Go straight.
No. What if there's like cars in the road and stuff like that?
He'll wait till the crosswalk.
She will die on the car because she's.
He went under the cars.
The chicken crossed the road at some point between the start and end. Somewhere in between there. That's what the intermediate value says. If you see a chicken on the other side of the road, guess what? Somehow, some way, he got over there, right? Yes? So somehow, some way, he eventually crossed the entire road. So what this means, intermediate value theorem, is that somehow, starting from here, ending here, you ended up at this point somewhere. No matter how you did it or how you hiked it, you somehow crossed this point right here.
Isn't it
You-
kind of like finding slope? Like if you have, like, say you're intersecting this one point, then you're trying to find a slope or something.
Kinda.
I don't know.
Okay, so now, do you guys agree that there's some place they cross this line right here, right? That's intermediate value theorem. Somehow they cross that. Somewhere, okay? To get all the way up here, you have to cross there. That's what intermediate value theorem is. Okay? So, use the intermediate value theorem to show that this has a 0 between 1 and 2. Okay? So, let's see. Intermediate value theorem is start by checking my endpoints. Where am I starting at?
1.
Okay, so let's see. F of
1.
1 is,
1 plus 1 minus 1. It's minus
so you
1.
said 1 plus 1 minus 1 minus 2.
Minus 1.
So we come up with what?
Minus 1.
Minus 1. Okay. And now check the other endpoint.
2.
You get 8? Okay. Intermediate value theorem says that we're checking to see if that there is a 0 between here and here.
Yeah.
Think of a number line. If you're starting at negatives, so if you're starting at negatives, so here's my graph. So he there, and then we are right here. So somewhere, somehow, it had to cross 0, right? Yes? Yeah. So were we able to prove it? Yes, because there is a change in sign. There is a change in sign here. So if it goes from negative to positive, hey, it crossed 0. If it goes from positive to negative, guess what? It crossed 0. There we go. That's all we're trying to do there. Intermediate value theorem is we're trying to see that somewhere in between there it will work. Does that make sense? Okay. All right, so let's try to finish this up. This is the last one right here. Calculator. X cubed, x squared. Okay. So let's go up here, clear this out. So x cubed plus x squared minus x minus 2. Yes. Enter. All right, so I have it here, right? Somewhere in between here. Okay, so that means that I only want to look, change my window, and let's go from 1 to 2. So it's somewhere in here, right? Okay, so now I'm going to show you guys the calculator trick on this one. So now we have this in our F1, right? So I'm going here, vars, F1, and we said 1, right? Okay. Do the same thing for 2, right? There we go. And I know it's somewhere in between there and there. Which one do you think it's closer to? Do you think it's closer to 1 or closer to 2? So let's try 1.5. Okay, that's positive. 1 point 1.2. There's a negative. Let's see. And let's do it again. 1.3. Hey, look, changes from negative to positive. So that means that I know I'm going to have 1.2 something, right? And then you just keep going on this. So it'd be, let's go 1.25. So 1.25, dang it. 1.25. It's positive. Let's see. I know. Okay. So you guys are going to play with this, and hopefully I'm going to see you guys advisory today, right? Okay. All right. So we know it's going to be somewhere between 1.2 and 1.3. And in our notes here, it says right here 3 decimal places. So we have to approximate it to 3 decimals. All right. Don't forget, like and subscribe.
No.